think there's still a few people coming, but in the meantime, maybe we can just say that if you actually missed out on yesterday, then everything is hosted online using the EdSTEM portal. So EdSTEM is this online machine that runs all of these Jupyter notebooks that we're running in the cloud, and so you get your own. You basically get your own VM that you can use in the browser, and we'll keep that available for about a week after this course. So if we don't get around to all the Jupyter notebooks, then yeah, you can follow along at your own leisure after the course.
Yeah.
Maybe I'll just
for those that are super keen, you can install pyGPlates onto your own system. And I don't think it's official yet, but we have a new release that has come out. Just like John Cannon has just released it. So I don't know if he's put a post on the GPlates website yet, but it's now available to download on the Earthbyte website, the new release. And I highly recommend using Anaconda of some sort to try and get all your dependencies installed if you're new to Python.
Yeah, 100%.
Yeah, it makes life a lot easier. You can even get pyGPlates to play along with pygmt if you're a GMT user trying to use Python. Yeah, it works really well for me, at least. I can't comment on anyone else's experience though.
Yeah, so we have included some like installation instructions here in the repo. Yeah, this is just under GPlates, pyGPlates course 2022 on GitHub. Yeah, so I've been using MiniForge, and Nicky's been using MiniConda. It doesn't really matter as long as you can access the Conda Forge channel to download packages. But yeah, Conda it's got some magic behind it, which means you don't have to worry about Python dependencies clashing with your own system dependencies. It kind of, I wouldn't say containerizes all the Python packages, but it puts them into a separate place on your machine, so that they all stay intact and uncontaminated from system Python.
Yeah. We will say pyGPlates isn't available on Anaconda yet, but it's in the works. So John Cannon is working on this, hopefully as we speak, but probably not. He works pretty late nights. And but so you'll have to link the Python pyGPlates package to your Conda environment. But once you've done that, your Jupyter notebooks, whenever you launch them, will always recognize that your Python environment will always recognize the pyGPlates installation. And there is a way to like link it inside the script, like your Jupyter notebook, using like import sys and then pointing towards where your pyGPlates is installed on your computer, or where the package contents are. Yeah, someone asked, what is Anaconda? Anaconda is like it's really annoying to name everything after animals because it makes it quite hard to difficult, because if you Google, quite hard to Google. If you Google Anaconda Python, you often get snakes, but it's programming, I guess it's like a wrapper, and you can download all your different Python and modules through there. So NumPy and SciPy and CartaPy that we used yesterday, you can install through Anaconda, and it makes it easy to kind of maintain everything. So if something gets updated, when you install that update through Anaconda, it makes sure that it won't break your other packages at the same time. Thanks, Chris, for adding that link there.
Yeah, so eventually, this step won't be necessary. We'll have a Conda install pyGPlates, and then everything will just work. Hopefully.
Yeah.
Okay, well, it's 5 past, so maybe we'll dive back into the EdSTEM platform. So to those who are just joining today, you would have received a link to the pyGPlates workshop on EdSTEM. And it would have taken you to this page. So to access the actual workbooks, so this is the discussion forum, but to access the actual workspaces, we click on this tab up here called Workspaces, and you'll see under public that I've created a workspace that's public access. So you just click on that, And then if you haven't already, then you have to click this fork icon, and that'll fork a copy of this to your own workspace. So, you know, it says fork workspace ? And you hit fork, not spoon or knife, just fork. Great. So let's go back into, I think we got partway through, oops. So this is my own personal workspace. So I think we got partway through introduction to pyGPlates. We started off with this introduction to Python. So this is good if you guys want to go through that and familiarize yourself with the common Python data structures. Yeah, it's kind of a baptism of fire to go from here to pyGPlates, but due to the nature of the course and how much time we have to be pretty prompt with this sort of thing. So Nicky, I think we got down to, where did we get down to?
We got, just finished this first part. Yeah, so we're about here now.
Okay, well, I'll leave it to you. So Nicky's going to go through notebook 2 and 3. I'll go through notebook 4, and depending on how much time we have, then Nicky will go through notebook 5 and 6.
Yeah, and the stuff will be left on GitHub as well forever until GitHub ceases to exist. So that if you ever want to refer back to everything and how we've done stuff, you can see the the figures that we make and everything. And
apparently some of the, yeah. Apparently some of the repositories on GitHub have been backed up to some Arctic storage vault.
Yeah, I think I have a badge for something. I don't know what that is, but
yeah, I don't know either. Yeah, but yeah, presumably it'll outlast human civilization. So that's exciting.
So yeah, yeah, but you can always refer back to them at any point in the future. And if things get majorly updated in pyGPlates, we'll hopefully do a new course with a new set of notebooks in the future. Okay, let me share my screen. So I hope you can all see that.
Yep, all good.
Yeah, okay. So let's just, so to start, we need to make sure we import something. So I've just imported pyGPlates. It hasn't complained and it's got a little 1 there, which makes it look like it's, so it was successful. And so I'm just gonna skip through these first cells of importing the rotation file. And you don't need to do, I'll just rerun them again. And so we're up to this part of, we're gonna create a point, but we don't know the plate ID for it. So we need to set the plate ID for it. And so this probably will be a lot of the data that most people would use because you don't know all the plate IDs off by heart. And so the easy way to do it, in my opinion, is to import this static polygon file. So these plate polygons, you can load them up in GPlates, and they have a plate ID associated for every part of the world. And so we'll just use the same coordinates from the first part. So I think this was Sydney and Melbourne that I picked. And then I've just put in a random point somewhere. We can add more points if we want. It's just a longitude and latitude of somewhere in the world. So let's go 70 latitude. So it has to be, well, I've got a lot of 30s here. Let's go 60. That's probably somewhere near Antarctica, I guess. And so to create the point feature, now that I've got my little list of my points, we can loop through and then we create this pyGPlates feature. And once we've done that, we can then set our geometry as a pyGPlates point on sphere. And so this is so that pyGPlates will now know, okay, we're trying to look at a pyGPlates object. And these are the attributes, that latitude and longitude. And then we'll just append it into a list. And so this is the magic line to assign a plate ID here, is this partition into plates command. I've even added a little link for the documentation up here for you guys. And so to assign these plate IDs, we need to give it that static polygon file, rotation file name, we give it the point features, and then we can also give it what properties we want to copy. So in this case, we want to copy that come on, EdStem, that reconstruction plate ID command. Where can I? Okay, there's that little bar. And then for this example, you can pick a time in the past. So I've just picked 40 million years. And we'll actually then, once we've assigned our plate IDs for the present day for these points, we'll reconstruct it into the past. And so, aptly named pyGPlates.reconstruct. And so I'll give it the point features with their plate IDs, a rotation file name, what I want to save those features to. So I'm saving it to a reconstructed feature geometry in this case that's empty, and a reconstruction time. And because pyGPlates won't just spit out the coordinates nicely for you, and it will tell you that you've reconstructed it, but if I run the rest of this cell, I'll just paste this here. So our output is not going to work if I paste it twice. So, our current output is some pyGPlates reconstructed feature geometries. And so to actually get those coordinates out, we do have to loop through again, and we can tell it we want the reconstructed geometry, and then we can convert that into latitude and longitude. And so this is just a little bit of a print statement so that I can print the present day coordinates and the reconstructed coordinates. And just, bear in mind, it's so the y then the x, not x then y, which always trips me up. So if I print this, so our present point, the first point was I guess this was Sydney, and it's moved a bit south. So we have a point here, I think this is in the Atlantic, and hasn't moved too much, I guess, because if it's the Atlantic, it's just going to move a little bit east or west. Can't do negative coordinates. And this point here is in a pretty similar spot as well, but it's definitely moved. So that's always good. I don't know what this is. So now we'll get to some more interesting stuff. We'll start reconstructing and plotting things. So this time we'll work on the coastline. So I'm just loading in a coastline file and a rotation file. And we'll got some reconstruction parameters. So your reconstruction time, again, you don't necessarily have to do this, but in case you wanted to change it, here's the anchor plate ID. I'm just going to fix it to 0 here. And this time I'll save everything to a reconstructed coastlines shape file instead of an empty list. So we can actually have the file and our feature. So you'll notice some files will appear up here. Similar to before, we just do that pyGPlates.reconstruct line. And so you can see it's created some shape files, or it's in the process of creating them. And so now, if I could download this and open this in ArcGIS or QGIS, or even import it into GPlates itself. So one of the things you probably want to do now is plot whatever we've reconstructed. So we import some of these plotting tools that will be helpful for us. So matplotlib, cartopy, and various parts of cartopy, you just read in that shapefile really nicely. NumPy, although possibly we don't use it. You don't necessarily need to do this matplotlib inline part in Jupyter Notebooks anymore, but it's kind of just habit for me at this point. So we'll import them and then start plotting what we've got. So I'm telling it here, I'm telling cartopy, this shape reader part of cartopy, to read in that reconstructed coastline shapefile that I just created, and then add that onto my figure. That looks great. Exactly what I was hoping for. And so, now we can, if you wanted to change that anchor plate ID, so everything we've done so far has been fixed to 0, so I guess to the spin axis, but we can anchor plate IDs so that you might want to fix Australia and see what everything moves around Australia. So in this case, we'll reconstruct the coastlines again. I'm just going to save it to a list so I don't create lots of files and EdStem crashes on me, although it might anyway. And I'll fix everything to 801, which is the plate ID of Australia. And then we'll plot it. So we'll plot those reconstructed coastlines that are saved as that list. And we'll also plot here CartoPy has a nice little handy command for just present day coastlines. And we'll plot them as purple so that we can see how they compare. Where did everything go? Well, that doesn't look good. Why is everything green? That's annoying. I have no idea what's happened here. Well, this should have worked, but CartoPy is clearly not liking what I'm doing. Any clue, Ben?
Yeah, is it, have you changed the, is it reconstruction time or no?
Yeah, possibly I did. I did change this at some point. Let's try. This is why I personally don't like CartoPy that much, but it is handy for Python. So something has gone wrong in my shapefile, but you can see that I've got my reconstructed geometries and Australia is in the same place. There must be an errant polygon in here that's plotting across the entire world that I have no idea about. Yeah. In the example on GitHub, I changed some of the stuff in this morning. In the example on GitHub, it did actually work though. Does anyone have any questions? I guess.
So yeah, Chris asks a question on, can you specify in pyGPlates to change the viewpoint of a mole-wide projection from equatorial to higher latitude, even polar? It will be very helpful for paleomagnetists. Yeah, so yeah, good question. So for the mole-wide projection that's built into CartoPy, you can change the central longitude, so you can, have 180 degrees as the central viewpoint. But so the default for mole-wide is that it's a global projection, so it shows the whole globe, just centered across different meridians. Having said that, you can specify an extent using ax.setExtent, and then just like choose a min-lat, also min-long, max-lon, min-lat, max-lat, and that'll
we'll actually do that. Yeah, we'll actually do that. We'll set our extent in the next notebook to limit. I think I've got a Mercator projection in this particular one.
Yeah, perfect.
So, yeah. For like really random projections in CartoPy, it's not as adaptable as like GMT might be, but you can export everything and plot it with normal GMT, or I've been playing around with pyGMT lately, and it does work quite well so far for what I've been trying, just the nice plots.
Yeah. Also, Chris, you can refer to the Introduction to Python notebook and click on the link that I provided to all the different CartoPy map projections. There are some polar ones there that are probably more appropriate than mole-wide for polar regions, and they have like equal area projections or equal equidistant projections. So yeah, whatever you're trying to plot, I'm sure CartoPy has the answer for you.
Yeah.
Okay. We have some other questions here.
Okay. It worked in the supplied workspace for Romana. That's great, because I don't know why it didn't work for me, but it definitely worked when I previously tried it. I did play around with stuff this morning and broke it, I think, in my haste. I need more coffee, apparently. And if I choose another plate ID to anchor, okay. So it's great that you're all getting stuff to work and you're playing around with it. This is really exciting. Okay.
Yeah. And what else have we got here? So how could we add ocean age? Yeah, so I don't think we actually bundle the ocean age grids in this, but we can definitely add grids to some of our maps that we produce.
Yeah, so
I think there are some examples later.
Yeah, in this next example, I'll add gravity. So it will be, conceptually similar to adding ocean age. there are, I guess if you wanted to add the ocean, I'm using just the images from the bundle data from the geodata. So I think we'll get to it in a second, but here I'm just reading in the vertical gravity gradient as a JPEG, and then I will plot that on our little figure. So you'll be able to see how we can do that. For adding the netcdf file, I tend to use Xarray as a package to import it. I'll type it into the chat. So there's Xarray. There's a couple of like variants on Xarray, like Rio Xarray, and I think maybe something else. It's also a netcdf4 package in Python, and they'll all play nicely with CartoPy so that you can add like the netcdf and then color your netcdf grid, your ocean age with whatever color palette you may like. If we have time, I'll try and show you an example, but we possibly will run out. But I can always add in examples onto the GitHub if you really want to see that done. Okay, so let's go into flow lines and motion paths. So hopefully you remember Sabin talking about flow lines and motion paths. And very coincidentally, we're going to use the same examples as what Sabin did, which was not at all planned. So we've got flow lines. They'll track the plate motion away from the spreading ridge, and they'll calculate using half-stage rotations. Motion paths track plate motion relative to a specified plate. I believe it's in stage rotations. So we often use motion paths for the absolute reference frame, to track like hotspot motion and things like that. So we'll first create flow lines, and I'm just going to import a whole bunch of different libraries that will be handy for this particular notebook. So you possibly, if you're doing this on your own system and also in EdStem, you possibly get this warning that I can't seem to scroll across. Oh crap! Scroll across for because my scroll thing doesn't work. Oh, there it is. So there's something that's incompatible. It says conversions will be slow, but it's not a breaking error. So I'm just going to ignore it for now. And so similar to if you're in GPlates in the desktop app, we need to create some seed points for our flow lines. So if you're in the desktop app, you probably click along a mid-ocean ridge for these flow lines. And so I just got in the coordinates for that mid-ocean for a couple of points, 4 points along that mid-ocean ridge along the South Atlantic. And so then we need to, if you remember when Sabin did this the other day, it'll come up with a dialogue where you have to assign your left plate ID and your right plate ID, and then a series of times. So here, left plate ID, I put as 201, 701 for my right plate ID, and I'm just creating my times between 0 and 120 million years ago in time steps of 2. So then now we actually create that flow line feature. And so throughout the notebook, I put in a whole bunch of links to the pyGPlates documentation for you in case you want to see what it says. So we can now just, add those seed points and make it a multi-point on sphere instead of a point on sphere on the previous notebook. And then we can just print out what those latitudes and longitudes are. And then we'll use that multi-point that pyGPlates now recognizes a multi-point on sphere and create a flow line using a particular, instead of just a feature, it's a flow line specific feature. So you can see that it printed out the same stuff. So we can see our seed points are exactly what we put in. So that's great. And I put these in latitude and longitude format this time just to make my life a little bit easier. And so now we'll actually create that reconstructed flow line. So right now, our flow line feature, you'll notice we haven't got any rotation file imported yet. So our flow line feature doesn't know what the rotations are. It just knows that it has these parameters of left plate ID, right plate ID. It's at this time, at these seed points, and it exists for these times. So now we can actually import a plate motion model. And similar to before, we'll reconstruct the flow line, but we need to make sure our reconstruct type, so that pyGPlates reconstructs everything correctly, uses a reconstruct type equals reconstruct type dot flow line. That's because flow lines are reconstructed in half stage rotations, because you've got 2 plates spreading, so you want to you don't want to overestimate your spreading or your flow lines on each side of the plate. And then we'll visualize things. So the best way to compare a flow line is to compare it to the fracture zones or compare it to some gravity anomalies. And in an ideal world, our fracture zones and or what we can see in the gravity will match our flow lines, or our flow lines will match our fracture zones, because the flow lines represent the spreading and fracture zones represent, is that trace of that seafloor spreading. So what I'll do here is I'll import a fracture zone GPMLZ. So this is from Wessel et al. 2015. It's a compilation of digitized fracture zones. And I really like GeoPandas to keep all my my geometries in, especially when they get a bit more complex. And so GeoPandas allows you to create, it's basically like a shapefile, but inside your Python notebook. And it works with some of the shapefile packages as well. So here's a little, we won't go into this in too much detail, but just to go through what this is essentially doing is going through these geometries and then getting the like the latitude and longitude coordinates, getting the reconstruction plate ID, their times, and then saving it to a geodata frame. And so then we can like paste out the contents. This is just the first 5 lines. So we've got a geometry of sorts that is in this line string format. So it knows it's basically converted into a shapefile format here of the line and with these coordinates. And I've just put the from age so that I can see if there's time dependency. We don't actually need that for this example, and the plate ID. And so to compare things, we can also add our gravity. So here's the gravity from the rasters in the geodata for GPlates 2.3. And I've just defined the image extent based on the longitudes and latitudes here. And we'll just read these into matplotlib as well. And so now we're ready to plot. So a lot of this is extra code just to make it look a little bit nicer in case you wanted to see how this was done. So we'll go through and we'll make it on a Mercator projection. And CartaPy isn't the most amazing at plotting ticks. So this is a lot of lines here to play around with my tick labels. So you can play around with the increments if you want. You can not plot them if you don't care about where you are in the world, or seeing where you are in the world on the map. And here we'll also limit the map extent. So instead of plotting a global map this time, I really want to just focus on that South Atlantic region. Next, we'll plot gravity. So I've told it to plot that gravity file that we just imported before, and I want it to be as a grayscale image, because otherwise it will try and apply the default CMap color map in matplotlib, which is Viridis. You'll get some weird like blue, yellow filter onto your gravity. We'll then plot just our present day coastlines. So this is using a CartaPy inbuilt CartaPy function to fill my coastlines instead of just plotting the outline. And then we'll plot that fracture zone GeoPandas array that I created here. So if I plot it, I can just do a little nice quick command here, go plot, and I can see those fracture zones. And so we'll add that to our axes, our figure axes, and make sure that we transfer them so everything is in the same coordinate system. And then we're finally ready to actually plot out flow lines on top. So flow lines, similar to the features, you have to loop through again to get your actual flow line coordinates out. And so in this example, we're going to get the times out because I'm going to color each point by how old it is according to the plate reconstruction model. And we'll plot the left, we'll get the individual coordinates for the left flow line out and the right flow line, and we'll plot them separately. And so you can see here, I've got the left flow lines, I'll plot as stars, and the right flow lines, I'll plot as triangles. And so here we go. So that looks pretty good, I think. Like you can see our flow lines are matching the black lines, which are our fracture zones. If we zoomed in even more, we probably could see a better fit. And it's hard to tell, but I don't know if that zooming works for you, but there are triangles on one side and stars on the other. So I'll give everyone a second I guess, to catch up, because I know we're going through this a bit fast. Yes, Chris, I agree that from age looks like old cheese. I always like say fromage in my head. It's I guess the default for if you're importing like a shapefile into GPlates, the application, it'll recognize some of these titles in cats, like plate ID 1 from age, to age, name in caps. And so you don't have to assign them to a particular column. So I'm in the habit of always specifying my oldest time is fromage. So does anyone have any questions? Any other questions? Everyone going okay? Okay, well, if we say we wanted to then find out, we know what our flow lines look like. We want to find a spreading rate just on one of those particular points. So the spreading rate across a ridge will vary depending on where you are, because it's relative to a pole somewhere. If you have a really big plate, you'll have slightly different spreading rates along the ridge itself. And so for ease, I'm just going to use one of my seed points, and we basically can create that flow line feature again and reconstruct it. So everything that we've done before. And then we can get the arc length arc length of each flow line segment. And because we know that we calculated our flow lines in 2 million year increments, we can then get the distance that flow line segment is. So that's what this line here is doing. So we have to multiply it by the mean radius of Earth, because we're not in, because we're using arc length, I guess. And then we can get our rate. And so because flow lines do half stage rates and we want our full spreading rate, we just multiply it by 2. And so here we get a nice little graph here. So this is for one of the points along the South Atlantic. So you can see slight decrease in spreading rate, and then it increases again, decreases. And so now we go to motion paths. So this is fairly similar to a flow line, except we just specify everything as a motion path. So you'll probably get kind of used to a lot of this syntax. So the C point, similar to before, just specify a C point. Here I've chosen the Hawaii hotspot. And then, choose your plate ID that's moving, your relative plate ID, and your time steps. And so in this example, I'm choosing plate ID 2. We're going to use a different rotation file this time. And there are some specific absolute reference frame rotations saved under the plate ID 2 in this particular file. Then, similar to before, we create a point on sphere, pyGPlates point on sphere geometry, and then we create that motion path feature instead with the similar kind of parameters for when we were doing a flow line. And now we're ready to actually create that the actual motion path geometry, so reconstruct it through time, similar to a flow line. And so this time we're going to use the Matthews et al. 2016 plate rotation file, which is from the GPlates 2.2 sample data. And that's because I wanted to fix everything to the Wessel and Kroenke absolute plate motion model, which is designed specifically for those specific hotspots. So we can see how that motion path fits the Hawaiian emperor chain. And so we'll create that motion path now here using the motion path feature that we already created. And the big difference here for this pyGPlates reconstruct call is this pyGPlates.reconstruct type.motion path. And again, I've included links for you so you can see some more information if you want to look at the documentation. And so now we're ready to plot this motion path. And I regretted doing this right after when I was creating this example, because I forgot that the Pacific is really quite annoying to plot across the anti-meridian in CartoPy, but I think it's useful, and it's all working now. So I'll just note that to do it in CartoPy for your set extent, CartoPy doesn't deal with the anti-meridian as well as, say, GMT, which is what I previously have used. And so I've specified here my longitude maximum as 210 degrees rather than -150, because otherwise I'll get the long way around the world, and we can show that as well. Plot again our our gravity that we had before. And this time to actually plot the reconstructed motion path, because we don't have different plates, we've only got one set of features, it's a lot easier. We can just go loop through that motion path that we created, and we just go get motion path to lat-long array, and then convert our our latitudes and longitudes. And I'll just also say, because CartoPy doesn't like plotting across the anti-meridian, converted a couple of the longitudes into 360 format, so that it doesn't plot horizontal lines across the whole world. So now you can see here we've got our motion path, and it's on top of the Hawaiian Emperor seamount chain. So that looks great. And as an example, I'll change this to -150 for a second. So you'll see we've plotted along the long way round, is what I would call this for the coordinates. So if you're working on the Pacific, which I've previously done a lot of work in, just be aware that some of the plotting packages really aren't as user-friendly as they should be, in my opinion. But you can always fix it. Okay, any questions? Yeah, so if you want to add more flow lines, yeah, just add more seed points. So it's helpful. I find it helpful in GPlates to use GPlates to look at where my mid-ocean ridge is. So I can just add more seed points and then copy those coordinates out. But you might have a whole bunch of points you specifically are very interested in that you could copy into. So now we'll look through. We can, similar to plotting the spreading rate for the flow lines, we can also plot the rate for the motion path. So similar to before, we get that the arc length, and then we multiply by the mean radius of the Earth. And then we get our rate, just dividing that distance by the time steps that we were using. So we knew, because we know what we've created our motion path at. And then our motion path will come out with the oldest time forward. So we have to just flip the order of our rate array. And so I should have cleared the outputs of this notebook before I ran it. So you get this nice little plot here. So we're going from 100 to 0 MA. There's a lot, increases in motion. So in tectonics, we often seem to visualize everything as a step plot, because we know we've got our plate motions at specific increments. And so to do that, you can modify your arrays that you're plotting, basically so it has duplicates in it, so that we know it'll plot at the so it'll plot nice lines for everything. So similar to this plot, it's just, stepified it. And alternatively, you can calculate the rate using a different function altogether here, using pyGPlates velocities. And we'll use this velocities function in a couple of the other notebooks as well. But just as you don't always have to say you just wanted to know what the rate of motion, like rate of this particular hotspot was, but you didn't want to have to create that motion path feature. You didn't want to plot it up as longitudes and latitudes. You can use, say, your seed point, or make it as a point on sphere, and then we can also get our reconstructed points out. So we can do things multiple ways. But you can basically, what we'll do is we'll reconstruct the feature, and then here we'll use the rotation model to get the rotation in stage rotations. So you'll see here we get the rotation between a time for a plate ID, and then between another time and a relative plate ID. And so this is, getting out our stage rotation. We can even print this rotation as well as I don't know if it prints in long. I think it probably prints in Cartesian coordinates, but you can print out that stage rotation that you're using throughout. And then you can then, once we've got our reconstructed feature, we can then calculate the velocity of it through time. So then we use that pyGPlates to calculate velocity, and we import that reconstructed geometry, our stage rotation, because we want to calculate the velocity in stages. and then get our velocity in centimeters per year. And because velocity outputs in the local Cartesian coordinates, we then can convert that into a magnitude and azimuth. So there we are. It prints it in something that's nice and readable. So you can see our stage rotations for each time that I think this was in 2 million year increments. So because I've done the time increment is smaller than the actual increment in the rotation file, you can see we don't really have much change in the stage for quite a bit of it. So this is all probably between 2 lines in the actual rotation file. And so then we can plot them on top and see how they compare. So this is the one that we just calculated from the velocity method there. And then this is the one from the motion path. And if I put them on top of each other, Matplotlib's clever and they'll change the colors of the lines for you if you've got multiple things you're plotting on the same graph, but you can see they plot on top of each other exactly. So that's excellent. And so say you wanted to compare plate motion models. So pyGPlates makes this pretty easy. So in GPlates, I guess you might have to create lots of motion paths and you have to redo all your points and then make sure you have fixed your rotation file to whatever layer that you're looking at if you want to look at the same time. But here we can just create another motion path feature. And so this time I'll use the rotation model we imported at the beginning of the file, which is up here, rotation model. And so this is just the latest rotation file from the 2.3 sample data. And you might remember a couple of days ago when we saw this in GPlates, it didn't fit the Hawaiian Emperor band because it's a reference frame that's created as an optimized reference frame. It's not calibrated specifically for the Pacific hotspots. And so in this particular plate motion model, we need to then fix it to the spin axis. 901 is the Pacific plate. And so we just go through the same steps of creating that motion path feature and then reconstructing it. And then now we can plot them on top of each other. So all this is similar to before, exactly the same code. And so we've got our original plate motion model here. So sorry, our original motion path, the one calibrated for the Pacific hotspots, that was saved as the M16 one. And then I've saved the new one as M19, and we'll plot that. And so one of them will be in stars, one of them will be in triangles. And so you can see we've get very different results, but bear in mind that the M19 model is using an optimized absolute reference frame. So it's not calibrated for the specific hotspots at all. So yeah, you could do this, yeah, all around the world if you wanted to, lots of different points, lots of different models if you want. Does anyone have any questions? Well, I know I'm going through this quite fast because I wanted to try and at least touch on most of the notebooks so that you can see how things are done. But if you do have any questions, please, yeah, add them to the discussion or the chat, or I think you could even add an issue on GitHub and I'll answer it there. Okay, well, I'll probably then, Ben, do you want to go through the fourth notebook?
Yeah, sure. Yeah. Okay. Let me share my screen. All right. Okay, so we've done motion paths and flow lines, and you know, that's kind of replicating the sort of GPlates functionality there. One of the things that that I work on quite a bit is to calculate the spreading rates and subduction rates across the globe. Now, for this, we're actually, so yeah, open up Notebook 4. So for this, we're actually importing another Python module, which is called Plate Tectonic Tools, or PTT for short. Plate tectonic tools is basically what the name says. So it does what it says on the tin. It essentially takes a whole bunch of pyGPlates functionality and wraps them so that, you know, within easy to use functions, so that you can, you know, query very simple stats on plate tectonics. So there's two main functions that we'll be using inside plate tectonic tools. The first one is to calculate the spreading rates in mid-ocean ridges. And the second one is to calculate the plate kinematics at trenches. So, you know, the trench information is actually a lot richer than the mid-ocean ridges. We get the location, the convergence velocity, the convergence angle. So that's the angle between the trench normal vector and the convergence velocity vector. The trench absolute velocity. So that's relative to the anchor plate. So the trench absolute velocity is how much the trench is moving. So that's quite useful if you want to start looking to details about trench rollback or trench advance. Also the trench obliquity angles, that's the angle between the trench normal and the trench absolute velocity. We also get the length of the arc segment in degrees. The azimuth angle, and we also get the subducting plate IDs and the trench plate ID. So all really useful stuff. Okay, so let's get started. Let's import all of these packages. So we've got our familiar favorites. We've got NumPy, we've got pyGPlates, we've got PTT, which is plate tectonic tools, matplotlib and CutterPy. All right. So as you'll start to notice, you know, these lines are repeated quite a bit throughout the notebooks. And that's because, you know, we need to tell pyGPlates which plate boundaries and which static polygons and rotation files to use. So we read all of these data into pyGPlates. You know, we've got our location to these files, and then we actually read them into pyGPlates just here. I'm also going to specify right here a tessellation threshold in radians, okay? So what plate tectonic tools does is it takes all of the trench segments and all of the mid-ocean ridge segments it sees within a particular time step. So like it loops over all of the topologies that you pass to it, and it tries to figure out, okay, which ones are tagged as GPML subduction zones, or which ones are tagged as, you know, mid-ocean ridges. And what it does then is essentially tessellate those topologies into little arc segments. And the length of those arc segments correspond to this threshold that we set here. So I've just set it to 0.5 degrees, which I've converted into radians. Okay, let's keep going. So let's just run this cell. Just to remind people that, you know, to run the cell, you can just press, hold down the shift and press return, and then it just runs the cell. All right, so here is essentially the boilerplate for calculating all these things. Yeah, so here's PTT here. We're accessing the subduction convergence module within PTT and the subduction convergence function within that module. So there's some of the naming could be a bit better, but what can you do? And that takes in a rotation file, your topology features, that tessellation threshold that I was talking about, the reconstruction time. So I've just set that to be 0, so the present day. And this is the velocity delta time. So that's like, essentially it averages out the plate kinematic data over however many millions of years you specify here. So, you know, you don't get, if you increase this number, then you should get smoother results through time. And we specify our anchor plate ID, which I've just set to 0. So that's the absolute reference frame. And then yeah, so we run this and then subduction. So what this returns to us is a whole bunch of different subduction segments with basically all of this information attached to it. And so I just want to put that into a numpy array, which I've done here. And then I can do, neat stuff like, assign the subduction longitude, latitude, angle, norm, etc. I've got the subduction length here. That was one of the returned variables. But to actually get that into a form that's actually useful, I want to convert the subduction length from degrees into radians and multiply by the mean radius of the Earth and get that into meters. So, it was in angles, in degrees, but now it's going to be in actual meters, which is a bit more useful. Likewise, for the subduction convergence, what I'm mostly interested here is the orthogonal convergence rate. So I actually take the angle here, so this is the subduction angle, and multiply that by the convergence velocity. So I get the trench normal convergence rate, which is more what I'm interested in. And also we get do the same for the subduction migration. So that's the trench migration. So again, we convert the trench normal angle into radians, or the cos of the radians of that, and then multiply that by the actual rate of migration in centimeters per year. Okay, so that's all of the subduction stuff out of the way. This part deals with the ridges. It's a bit shorter, and it takes basically exactly the same inputs. So, we've got our rotation file, our topology features, reconstruction time, tessellation threshold. Here we're actually specifying the GPML type, which is mid-ocean ridge. And again, we've got the anchor plate ID, which is equal to 0. And here we get our longitudes and latitudes, the velocities, this is actually the spreading rate, and the ridge lengths in meters again. So if we run this cell, we'll actually get a whole bunch of warning messages being printed out. Now, these are mostly diagnostic. Essentially, what it's saying to us is that, most of these, the subduction polarity is not properly set within the rotation file. So there's some problems with how Plate Tectonic Tools is reading one particular subduction segment. So this is a kind of diagnostic, more so for like tweaking the rotation files to make sure that we've properly resolved all of these topologies. But, if we consider that there's about a handful of these warnings for a handful of subduction segments, it's actually not too bad. So I'm just going to ignore those for now, but note that, pyGPlates and Plate Tectonic Tools does give you some feedback, which can be useful. Okay, so you've seen this before. Nicky showed this in notebook 2. Essentially, what I want to do is reconstruct the coastlines to a particular time. In my case, so I've set reconstruction time to 0. So, this is mostly unnecessary. So I'm reconstructing the coastlines to the present day. But, if we change what the reconstruction time is here, then we get to change, we get to reconstruct those coastlines further back in time. And what this essentially does is it defines our shapefile that we want to output to. And then we just, we use this pyGPlates.reconstruct function. So, we've got our coastline file name that we specified earlier, the rotation file name, this guy, the name of the shapefile that we want to output to, our reconstruction time, and anchor plate ID. And when I ran that cell, you can see that the shapefile was actually created here in my workspace. So, later on after the course, if you wanted to, you could download these documents or the shapefile and you could use that in pyGMT or GMT or quantum GIS, whatever you like. So yeah, that's good. Okay, and then once we've reconstructed those coastlines to the shapefile, we have to read those back in using the shape reader, and we convert that to a CartaPy feature type. So CartaPy can manipulate that shapefile. Okay, so yeah, so I've run that cell, and I'm going to run this cell as well. And what I've done here is I've set up a figure. I've set the projection to a mole-wide projection with the central longitude being 180 degrees. And I've got two scatter plots. The first one is visualizing the subduction coordinates in longitudes and latitudes. And it's coloring each of these points by subduction convergence. And I'm multiplying it by 100 to get to centimeters per year. And I'm specifying the Viridis color map. So there's lots of color maps to choose from in Matplotlib, but yeah, Viridis is a good one. It's one of those perceptually uniform color maps, which are so good. And then I'm doing the same for the mid-ocean ridges, except I'm specifying the spreading rate here, and I'm choosing the magma color map, which is very fitting. Okay. And what we have here then is, then we add our coastline. So that's our reconstructed coastlines. And I've got my two color bars here. So yeah, it looks pretty good. We get our subduction zones where we ought to get them, and our mid-ocean ridges. And we can see the variation in spreading rate and convergence velocity at each of those segments. Are there any questions about that so far? No, still got everyone? Excellent. Any questions in the chat? No. All right. Let's keep on moving. So now that we have that, we've actually computed all the ingredients necessary to compute the rate of crustal production versus crustal destruction. So we can estimate how much new crust is being formed at each time step, and also how much oceanic material is destroyed, so recycled back into the mantle at each time step. And to do that, it's very simple, right? So the area subducted by trenches over 1 year, we can calculate by essentially summing the subduction convergence rate multiplied by the subduction length, so that the length of the arc segment for each subduction zone, and multiplying by 10 to the negative 6. So that converts from millions of years to years. And we can do the same for the rate of crustal production. So ridge velocity times the ridge length times 10 to the negative 6. And so we can print these out below. So the destruction rate is 2.7 kilometers squared per year. Production rate is 2.91 kilometers squared per year. And we can take the ratio of production to destruction, and they're roughly it's just above 1. So that's kind of reassuring. I've done something here to make it all opaque. What have I done? Well, anyway, I'll try to get this back online. There's a little exercise here, and that is to plot the mean spreading rate and convergence rate over the last 100 million years. So we've kind of gone through how to create functions before. That's kind of a useful starting point. So you kind of create functions to retrieve the convergence rate and the spreading rate using plate tectonic tools. And then you kind of create a loop within that to calculate that over time. So we'll just, we'll go on with that for a couple of minutes, and then Let's compare notes. Yeah, so there's a question in the chat. Yeah. So yeah, I think there's a bit of confusion here about which color map belongs to which feature. So that's not a subduction zone, that's a spreading ridge. It just looks dark at the lower end of the spectrum here. All right. Do we have any questions on that little exercise so far? What I might do is show you guys kind of what I mean when I'm talking about creating functions. So let's just paste this back in here. And now what I want to do is actually indent these lines. Now, I haven't told you guys how to do this without having to put spaces in every single line. You can just highlight the passage of text that you want to indent and then go Control and then square right bracket. And that shifts the whole thing right, one indentation. So then we can do something like this. Define our function, subduction info. And it's going to take one argument, which will be reconstruction time. Okay, and let's do the same here. And define our function with good spreading info, and it takes one argument, which is reconstruction time. Now, don't forget that we have to return something from these functions. So in this case, we're interested in calculating the spreading rate and the subduction convergence rate through time. So I'm just going to return those. So return subduction convergence. Perfect. And then here, I'm going to return ridge velocity. Okay, so I'm just going to run that. Great. So we've defined our functions, subduction info and spreading info. Perfect. So now if I actually run those, subduction info, then I get a whole bunch of numbers that correspond, whoops. Yeah, that correspond to the subduction convergence velocity for 0 million years. So the present day. Cool. And the same will be true if we run this function here. So what I might do now is create a for loop. So for time in, let's say, let's create a list of times from 0, 20, 40, 60, 80, 100 million years ago. We want to find out, we essentially want to run our functions. So subduction info, and pass the parameter time. I'll just call this convergence velocity And then spreading velocity is equal to spreading info. Whoops. Spreading info. Oh gosh, what's happened here? Spreading info time. Okay. And what we also want to do is to be able to save these variables. So what we can do is actually make a spreading velocity list, and we can just create an empty list like so, and convergence velocity list is also an empty list. So then when we calculate these parameters, we can actually append them to the list. Yeah, so let's do that. So spreading velocity, I don't know how it does that. Spreading velocity list. It's done it again. Spreading velocity list dot append, and I want to take the mean of the spreading velocity for that time step. So spreading velocity dot mean, and then I'll do the same for the convergence velocity. Okay, now I'm just going to run that cell, and it's going to do its thing. So yeah, it's already completed that task. So now let's visualize our output. Okay, and that's going to be pretty easy. I'm just going to create a new figure using matplotlib. I'm going to create an axis on that figure object. So fig.add subplot. And then I'm just going to specify some labels here. So X label equal to time. Y label is equal to velocity. These should be strings. Okay, now I realize here that I haven't actually specified, so I've just created a list of numbers here. But what I can do to make this more general is have call this time steps and define time steps above here. Okay, there we go. So I'll run that again. And now what I can do when I plot them is I can specify time steps here. And I'm going to set the first axis is going to be spreading velocity list. And then I'll create another plot next to that, also taking the same x-axis and then plotting the convergence velocity list. Cool, there we have it. So yeah, this is in meters per year. We have to multiply that by 100 to get centimeters per year. But yeah, that's kind of a general way of how you'd implement this sort of routine through time. You can increase the resolution of that, so you can instead of specifying these time steps manually, you might decide that you want to actually do it for every million year, and we can do that by creating a range of numbers. So a range of numbers from 0 to 100 with a spacing of 1 at each interval. And then of course this routine will take a lot longer, but yeah, instead of having this kind of blocky looking plot here, we'd have a much more richer, lot more rich information between each of these time step intervals. Okay, does anyone else have any questions on that? Nicky's been answering some of these questions, which has been great. Yep, yeah, so we can have separate maps for extension and subduction. Yeah, that's pretty easy to do. And I think Nicky's going to take us through an example of a figure with multiple subplots in the next notebook. Yes, so how do you make a layout of the subplots? We could just do it now very quickly. So we go plot.subplots. And then here, I think we specify the number of rows, the number of columns, and then it returns a figure at the front, and then axis 1 and axis 2. I think that this should actually work. Then we don't need to actually have that anymore. And then let's just see if that works. Yep, there we go. So that's two subplots. Top one is the spreading velocity, and the bottom one is the convergence velocity. Yeah, and as we can see, since I've run this cell up here with 1 million year increments, we get much richer information within these graphs. Cool. So that kind of, in this exercise, we've learned how to define our own functions, return the information that we're interested in, and then repeat an analysis over multiple time steps, and then plot the results. So I hope that's been helpful. I might pass back to Nicky now to run through notebook 5.
Thanks, Ben. Okay, let me share my screen. Okay, can you see that all fine? So I'm on the subplot page. Everyone can see that? Well, no one's objecting, so I hope so. Okay, so this time we're going to reconstruct even more features. So we'll reconstruct some data from the paleobiology database. So similar to before, we'll import our modules. So we get the same warning for the Shapely, but that's okay. And so you can download your own data, or we've provided the data as well downloaded and with some of the columns removed. And so in the paleobiology database, you can actually download straight from a URL if you know what you're looking for. So here's the URL for the data that we're going to be looking at. And you could use this line here to read in that CSV. It could take a little while. So for the sake of time, we've actually specified that CSV here. And so if we have a look at what that is, we can go to the GitHub, go into data, and we can view that raw data. So you can see this file is 10 megabytes. You can import your own data that's even more. And this data is a CSV, and it's got a whole bunch of different columns. So you can see it's got an accepted name, max time, min time, a reference number, longitude and latitude, and environment. Okay, so let's import that data into Python, and we're using this package. I don't think we've used it yet, called pandas here. And so I guess I don't know if we said, so you could import these packages and just go import pandas like this, but then every time I want to use that package throughout my code, I'd have to type in pandas out in full. So using as PD, there is that little shortcut. So I don't have to type out as much all the time and make my code really long. Okay, so that's imported all successfully, and so we can have a look at what's in this data frame. So nicely laid out compared to in the browser, but you can see we've got the occurrence number, an accepted name, the times, the reference, latitude and longitudes, and the environments, the paleo environment for these fossils. And these are present day coordinates, that longitude and latitude. And so in this exercise, what we'll do is we'll have to assign some plate IDs, and then we'll reconstruct them into the past and plot them up. So this would be similar if you had your own data and you wanted to display it in GPlates. You could even use this code to convert it into something GPlates friendly, and then create a shapefile, and then you could load in that shapefile into the GPlates desktop app, or you can, it's really handy to be able to do this with your own kind of data. So we've got here, you can see we've got 141,000 rows. Originally, I wanted to do this for the whole Cenozoic, and it was like over 500,000 points, and the EdSTEM environment did not like me trying to get that many points reconstructed and shaping the shape files all the time. So it's still a lot of points, and this is just for the late Cretaceous. And so if you had downloaded the actual CSV from this link here, which is what this is based on, there's a lot more rows in it, and so sorry, a lot more columns in it. And so pandas makes it easy to kind of check, what are our columns if we've got, if you had like 50 columns instead of 8, it would just kind of appear off the screen, and so you wouldn't be able to see very much. So we can see as a nice shortcut, we've got those 8 rows, and those are those names. Because we've also imported the environments of these fossils, you can see what the unique environments are. So it won't, we could print out environment like this. And we get the environment column for everything. But if I wanted to just see what are the types of environments, we can print them all out here, so we can see what are the possibilities for this data set. And so here we're next gonna, there's a lot of environments here. Yes, we can, 68 environments. So that's a lot. And if you were plotting that on a figure, your legend would be insane and probably wouldn't be able to tell what environment is what. So for the sake of this exercise, I just want to know what's a marine environment, what's on land, and then some of them might not fit in because I didn't specify it. So what are the ones I've forgotten to do? So I've created here a little function, and I'm just going through if an environment is marine, indeterminate, carbonate, peritidal, et cetera, et cetera, et cetera. I'm just going to give it this overall value of marine. And then same for if it's terrestrial, fluvial, et cetera, et cetera, et cetera. I'm going to give it terrestrial. If it's glacial, give it its own value of glacial. And then if I haven't specified it in anywhere up here before, I'll go not specified. And then just in case I've done something, if it's not specified in the file at all, if it's just blank, then that becomes a not specified. And then if I've forgotten an environment from this whole long list of going through, I'll give it a value of skipped. So let's run that cell. So you can see here in the top left, if there's no number in this cell, it means it hasn't been run yet during your Python session. So now it says number 10. And so now we can apply that function, and I'll apply it on the row, so axis number 1. And we'll just add all that data that the new environments is a new column called environment broad. So we'll run that, take a little bit because there's quite a lot of rows. And great, so it's finished. So now we can just print that data again and see what's in it. And we can see we've got this new column, environment broad, with just a few different types of environments in there that we are ready to do stuff with. And so now we've just been using pandas so far. So now let's actually reconstruct things with pyGPlates. So similar to other notebooks, I know you're kind of getting into the habit of just copying and pasting these lines almost. We'll load in our rotation file, our static polygon file, our coastlines, just the one we plotted. We can see where things are in the world. And then we'll just read them into pyGPlates. And I think a lot of the functions don't actually require you to do this step. You can just use the file names directly. But out of habit, I'll read them as rotation models and feature collections. And so to reconstruct our paleobiology data, you remember it's still in a data frame. It's basically still a CSV. And so we need to get it into a format that pyGPlates can reconstruct. And so we need to convert that into a pyGPlates feature. And so what we'll do is we'll loop through each row in our paleobiology data, and we'll assign a point on sphere object using the row that we're of the data frame, the latitude and the longitude. And then we'll create a feature and set that the geometry of that feature to that point that we've just from that point on sphere object. And so in pyGPlates, you can also set a whole bunch of other attributes that aren't default to pyGPlates that you want to preserve. So this is similar to, I use a lot of shape files, and conveniently in pyGPlates, for me, it's the module or the function called set file shapefile attribute, and so you can include all of these things into your pyGPlates feature, and it will preserve that when you reconstruct it or do any work with it, and I can get those attributes out later. So here I've just given it a few different ones. So I've given it the accepted name, so that's the fossil name, the environment, so that one of those 68 environments that we printed earlier, the broad environments that we just assigned, and the occurrence number, just because we'll add a bunch of numbers. And we can also set that valid time of the feature as well. So if we remind ourselves of what are our column names, we've got the max MA and the min MA. So we can set that on our feature is using the set valid time. And then we append it all to a paleobiology PBDB point features empty list that we have here. So let's do that. There's a lot of points, so it might take a couple of seconds. And you can see it's running while it's got this circle with a square inside of it. Peter, so it looks like pyGPlates is not defined. So that means it doesn't know what maybe you haven't moduled imported your pyGPlates module in yet. So Python tries to be helpful and gives you errors that sometimes they're not quite helpful, but a lot of the time, yeah, it will give you errors so you can try and trace back where it is. Yeah, and the kernel crash. Yeah, so I tried to limit the size and it's a lot of points, and the EdStem environment doesn't have heaps of RAM, so we'll see how this goes. When the kernel crashes, it kind of forgets everything that you've done. You have to import everything all over again, so it's a little frustrating. So if you were doing this on your own laptop, you probably wouldn't have this this issue, assuming you have a modern laptop that I guess my laptop has 64 gigs of RAM, so I can I get a bit over ambitious as to what cloud computing can do because it's my laptop. We'll see how I go, and then yeah, I think if everyone's trying to do it at once, it might be angry. I've never used the EdStem environment before this, but yeah, but your error I think is coming up because of your kernel crashing is because there's not enough memory or not enough RAM for everyone. So let's try this. The next step is to assign those plate IDs. So we did this previously in the second notebook, and so we'll again use this partition into plates function, and we'll use those paleobiology data point features, and we'll copy over that reconstructed plate ID. And I've just added this cell magic here. So anything which has 2 percentage signs at the front, you can access a few different functions for the cell itself in the, I guess, the Jupyter environment. And so it told me that my wall time is 24.1 seconds. And so this was, if you had maybe loaded in like 500,000 points, it might take a bit longer. And if you're trying to do this repetitively, you might want to know how long your cell might take for some of these points, for some of these sets. And then you can kind of time your coffee breaks if you're running a bunch of things at once. And so let's have a look if this is, we've got a lot of pyGPlates features now. I'm going to clear that because you can see that's what's in our cell. Okay, and so now let's reconstruct this to 83 MA. So hopefully this works with the amount of memory and space we have. So, oh, nice and quick. So similar to you've seen many, many times now, we'll use this pyGPlates.reconstruct function, and with our reconstruction time I set to 83 MA, and the output I've saved as saving to this list that I'm creating inside here. using that rotation model that we imported earlier. And yeah, there's our reconstruction time. So you don't have to specify that anchor plate ID if you don't want to. But if you don't specify it, it's just going to do everything relative to 0. So that's run successfully. And so now let's convert these points into a geodata frame. So you remember we had all these shapefile attributes, and we originally had it all like this with some nice columns. And so basically we're going to convert it back into that format, but we're going to have another column instead of longitude and latitude as their own separate columns. We'll make it as a geometry column, and that way we can it's basically like a shapefile in your little Python environment, and it makes it really easy actually to save it out to a shapefile in the future. So I've provided this little function for you. The inputs are that reconstructed geometry and just reconstruction time, just so I don't forget it. And I've just assigned an empty geodata frame with a whole bunch of columns that are set to none. And I've set the coordinate reference system to be WGA. That's 84. So just the global one that GPlates uses. And so in this function, we'll go through that reconstructed geometry. We'll get the point, and then we convert that into latitude and longitude, and then write those longitudes and latitudes into our rlat and rlon for reconstructed lat, reconstructed long. And I guess down here you can see we then convert that into a shapely geometry that's a point type. And so I don't know if I showed, so when we imported our shapely geometry, we imported point from this package. So that point with a capital P is actually something we imported. And we'll append our geometry there. And then we'll also get out a whole bunch of our other attributes. So we'll get the valid time from our points, and the valid time actually has your from age, your from age, and your to age saved in it. So I'll save that to my empty lists here. So the first number is from age, and the second number is to age. And remember that Python counts from 0. And we'll get our plate reconstruction ID for all of our points as well. So just using that get plate reconstruction plate ID. And then we'll get our other attributes. So this is particularly handy if it's your own data set and you have lots of columns that you really want to preserve. That it's not a plate ID or a name or something. So before we used up here, we use set shapefile attribute. And so this time we'll use get shapefile attribute. Some nice symmetry there. And we'll get the shapefile attributes for what we set earlier. So we set our accepted name, our environment broad, and occurrence number. And so you should have to make sure you've got the same spelling in the strings here. Otherwise it won't know, if I use environments, it'll get confused and it'll be empty. So we'll add all of this to our list, so that using that, our empty lists. So here's accepted names is empty, and we'll just append that there. Once all of that's done, we'll write that information to those different columns in our geodata frame, and then we'll return that geodata frame. Okay, so now Python knows what our function is, and so let's actually apply that. So I can see this. Okay. So we've got our geodata frame here, and you can see name is Nan. We didn't actually ever set a name, so it's returned as Nan. We've got our plate IDs, our from age, our to age, our accepted names. So that's what came from the paleobiology database, CSV, the original environment, our broad environment that we added, and then our occurrence number from the original CSV. And then we've got here our geometry. So this is the point, this is a shapely geometry, point geometry, and it's got these coordinates. So you can see all the coordinates there. And just so I don't get confused at myself as to what my geodata frame has my geometries at, I also added reconstruction time, so I know when I've reconstructed these points too. And so just a little note about, for geodata frames, you need to have this geometry column as a lowercase geometry, and that will be whatever the geometry that it will recognize. And so now we can use GeoPandas to just really quickly plot this. So I could do, it's a slightly fancier plot, so I just go on geopandas.plot, and I want to color everything by that environment broad column, and I've just added that legend. You could also do just GeoPandas plot just to, you might want to sanity check that you even have data in there. We just do plot without any options, and so we can see, yeah, we've got some stuff in the world. And then now we can save that all to a shapefile. So it's just our geodata frame, and then to file, and we can save that to, I'm saving that to a file called reconstructed pbdb data with a little sub thing, so I can put my time in there, ma.shapefile. And so you can see it's creating, it's in the works, but it's creating this shapefile for 83 MA. And then that could be imported into GPlates if you wanted to, and that's your file. Your own data reconstructed to 83, ready for visualization in GPlates if you prefer that way. It might take a little while because it's probably not the smallest. And you do get this warning because I'm saving it to a shapefile. Column names longer than 10 characters will be truncated when saved to an Esri shapefile. That's a shapefile limitation. So it is sometimes handy to shorten these names, and you'll, like, this will definitely be cut off. I think environment gets cut off to environment, not environment. So you can rename your columns in GeoPandas before you save them. It's still going, I think. There we are. So it's finally finished. Now let's reconstruct some coastlines, because it's a little hard to know. Like, I can kind of broadly see this would probably be America, here's South America, but it's a bit easier when we have some reconstructed coastlines just to guide us, especially if you are using a data set that would is completely different, where it's going to be. So let's reconstruct those coastlines again, and we've done this before, so you should be pros at this by now. That pyGPlates.reconstruct coast, and we've got that import coastline file, rotation model, and the coastlines, reconstructed coastlines that we're saving, the empty list that we're saving to. And now let's plot it up. So we can, I tend to define a lot of my my colors and my line widths and stuff separately, so I don't, if I'm doing this lots of times or doing it for a subplot, I don't have to like modify 10 lines of it or something. So I've just defined a marker size, the edge width, the alpha, so the transparency, and then we'll start plotting. So here's our PLT figure, matplotlib figure call. I'm telling it I want to set it as a Robinson projection, and we'll set this as a global thing. I'll plot some present day coastlines on there as well, just for reference. And then here we are. Here's our plot reconstructed coastlines call. So we'll start with getting our coastlines for plotting. We've got a whole bunch of polygons, so we will loop through and we'll wrap those polygons so that they hopefully don't do weird things and cover the whole world, because it becomes issues when you're crossing the dateline or the anti-meridian as well. In CartoPy, it doesn't quite like it if you've got lots of coordinates crossing, and so you end up with those horizontal lines. So that's what all of this is doing. And then we'll add that geometry onto our plot. And so then the next part is we'll plot our fossils. So you've already probably seen, we did this earlier, we just use plot, but now we'll actually pass a whole bunch of arguments to it. So we'll plot it on our axes that we set up here. We want to plot it by that environment broad column. We'll specify a blue, red, green color map. That alpha color that we used earlier, I actually don't think we use this marker edge width, but we'll make our fossils have a black outline, so K is that shortcut, or you could even write black here. We'll make it marker size, and then we've got to transform it so that it knows it's the coordinates, and we'll add a legend to it as well. And then we'll just add a little title with the reconstruction time, so we know when we've reconstructed our fossils too. great. So you can see here we've got in the filled grey, we've got our reconstructed coastlines. So Australia's moved a little bit closer to Antarctica. In the hollow grey, we've got our present day coastlines. You can see how far things are off. And then we've got anything that's in blue is probably a marine, fossil of some sort. Anything in green was on land, and then a whole bunch of red ones which was skipped in my process. So maybe my function didn't have everything that every environment type from the paleobiology database environments saved within it. So does anyone have any questions so far? There's a few in the chat I can see. So yeah, you can save it. Yeah, we can save our plots itself. We can do a PNG, and I think we do this in the next notebook actually. Save fig test.pdf, and it should come up with a PDF from the side. Did it finish? Yeah. Perhaps Edstone doesn't like PDFs. Try a PNG. Oh wait, that's not a PNG. Okay, errored because it doesn't know what a PNG is. Okay, there we are. It's so here's our that PDF. I don't know what happened to it. Oh, there I just was too impatient when I opened it. So so we've got this PDF. I think it's missing some lines. Maybe this is the EdStem missing it because it doesn't normally look like that. But you can import that into Illustrator, and then that will be a vector. Or we've got that PNG here already saved as well. Okay, and so now we'll plot things on multiple subplots. So I know there was a question in the chat earlier. So for some of this, what we're gonna do is that we're gonna reconstruct fossils to a few different times. And so I want to plot that as subplots so I can see where they are at these different times. And so what I've done here is I've created a new function, so that def, and I'll actually plot as part of this function as well, so that I don't have to just copy and paste this code 4 times. I think that's what we do here. And so as part of this function, we'll tell it a reconstruction time I want to make it at, so that I can reconstruct my fossils to that particular time, and then the axes that I want to plot things on. So yeah, similar to before, I think this is all literally just copied and pasted from earlier, and then indented. We'll reconstruct our fossils, reconstruct our coastlines, and then we'll plot all of these things onto whatever axes, and then we'll set the title to be that reconstruction time. So let's run that. And here I've set up, I'm using plt.subplots for mine. So I want 2 rows, 2 columns, and each axis that I'm using, so the third number in the subplot call is which number of that subplot. So it will go like top left, top right, middle left, middle right, and so on. So my first axis, I'm going to plot 100. I want to reconstruct and plot things to 100 million years ago. My second one will be 90, third one will be 80, and then fourth one will be 70. And so, might take a little bit because it does have to reconstruct everything 4 times. So I could, as part of all of this, I could save out this reconstructed fossil shape file in those different increments. I won't here, but yeah, save them out, and then I could put them all into GPlates or into ArcGIS, let's say. And so this is what we get. So you can see we've got our reconstructed coastlines, like they're moving 100 MA. Look like we're haven't quite opened the South Atlantic, or it's starting to open. Whereas versus 70 MA, they're much further apart. And you can see our fossils are moving. And for reference, I've just plotted present day coastlines on here as well, so we can kind of see what's happening, where everything is relative to present day as well. So hopefully that's answered the question about those subplots as well. And you can do even more crazy things with these. And I could have a color bar here if I wanted to, or I could have different projections if I wanted to. Yeah, you know, the world's your oyster. And so let's now, because we've got everything in our, we've got a whole bunch of accepted names in our geodata frame. Say you're particularly interested in just one of these. So I've just picked gastropoda for gastropods. And so we can actually filter this data and just get everything that has that gastropoda accepted name. And you'll see that we've now subset our data to be 88 rows instead of what was it, over 100,000 points, 100,000 rows before. And so I can calculate, I know that I've assigned that from age and to age earlier so that it will appear for, I can't do this mental maths, but some amount of years in GPlates if we were reconstructing the point. But say I just want to get that average age and I want to plot it on a map. So at 83 MA, the gastropods, the average age of what those gastropods are, and I guess I haven't subtracted 83 or anything like that. This is just from the fossil data. So I'll just get that average age and add it as a new column. So the average age of a lot of those different fossils. So now we can plot this again. So we'll, similar to before, we have that marker size, we've got that figure. And then here's this, the difference. We've got this gastropod geodata frame, and I'm plotting that column of average age. I'm using the color map Inferno this time, which I quite like. I've also applied a couple of, I want to plot a color bar this time, and so I've told it to plot the legend, and I've given it some keywords to that legend. So I'll label it with average age and this shrink pad aspect orientation are just to make it look a little bit nicer. And then we'll give it that title again. So I don't know why I went to the top. And here we are. So those are gastropods at 83 MA. And you know, similar to what we've done in other notebooks, you can change this longitude equals 180. So I, could have plotted it this way. For fossils, it's probably, for this particular data set, I think probably having 0 as the central longitude is a bit better. But yeah, so that's how you can reconstruct your own data set that's not already ready for GPlates or pyGPlates. And then you could download this file and then open up in your own GPlates, open up in GPlates itself. And this would, just bear in mind, this one would be at 83 MA. So you might want to, you could download that file. You could create that file for 0 MA with the to age and from age columns already assigned, and then reconstruct it through time quite easily in GPlates. Does anyone have any questions? Okay, well, there's one more notebook and there's 15 minutes. So I'm just going to delete all of this. So let's see if we can race through it, because this will create an animation in this one, which will be quite cool. So similar to before, we'll import a few different libraries, and we'll import our rotation files. So we'll also import these topologies. These are all from the sample data again. And then because we've got 3 files we need for the topologies to work, don't just try one, because you'll find that it looks a little strange. We need to add them into a feature collection, like overall feature collection that I've first defined, and then I'll loop through and add each file to that feature collection. And so in this notebook, we're going to calculate a whole bunch of, velocities across the world and plot a whole bunch of arrows and then animate this all. So to do that, in GPlates, we would create those velocity domain points, and there's a little interactive thing. And so we can do something similar in pyGPlates. So I put this function to create a multi-point on sphere for a whole bunch of longitudes and latitudes. And then I tell it I want it to be a GPML mesh node, so that it's we can start creating our velocity domain features. So let's run this and we'll actually apply this. So we'll apply that function here and we're going to make a grid at 5-degree increments. So we'll use that a range function in NumPy again. We'll go from minus 180 degrees longitude to 180 degrees in 5-degree increments. And then same for the latitudes, minus 90 to 90 in 5. And so now we'll calculate the velocities at all those points. So we haven't, I don't know what the plate IDs for all of these points are. And so we need to tell GPlates, pyGPlates somehow what plate ID they are so we can calculate their velocity. So I've given you the links to all the different things that we're using here. Some of these will look familiar. So I think I've already used all of them. That plate partitioner, we actually did use that get rotation in the motion path one. And we've already used that calculate velocities very briefly. And then it will do everything in the spherical coordinates. We need to calculate it into things that make a bit more sense, convert those velocities into something that's a bit more readable. So here I'm setting up my time step, my delta time, and I'm setting up my plate partitioner. So it's based on my topology, so I know how to assign my plate IDs. And then we will loop through the points, that 5-degree mesh that we just created. And then for each of when we loop through, we'll get the geometry and then we'll get the point. And so then we'll actually get the point out and append it to an empty list. Then we'll assign the plate ID for all of those points based on those topologies. We'll get the reconstruction plate ID, and then we'll get the stage rotation at that time in the past. So it's you can use this get rotation to get it an absolute a finite rotation, but it's in case because we've got time to time plus delta time instead of 0, we can get the stage rotation, and then we'll use that to calculate the velocity for those domain points with that stage rotation. And so the last point here is we'll convert everything from geocentric to magnitude azimuth inclination. So it will give us a tuple out with magnitude azimuth inclination in it. So let's run this. There we are. And so if we have a look at all velocities, we've got a whole bunch of tuples in it, but and so what we can do is we can loop through and get the magnitude and the azimuth separately, and then we can also go through our domain points and get that longitude and latitude, so it's a bit easier to plot later on. And so now we're ready to plot. So here similar to before, we use this figure, we add an axis. I seem to always choose Robinson, and this time I've put the Pacific in the center. I'm just adding my present day coastlines and adding some grid lines this time to our figure, and setting a global extent. And then we'll plot a scatter plot of the longitudes and latitudes from our 5-degree grid, and we'll color it based on the magnitude of that point. And we'll add a color bar. So here we can see Pacific is quite fast, and you've got lots, slower magnitudes, velocities in the Atlantic. But you might want to actually use velocity vectors for all of this. So to do that, we do the exact same thing as before, but instead of this convert from geocentric to magnitude azimuth inclination, this time we'll use convert from geocentric to northeast down, so that it's in the format that is a bit easier for plotting vectors in CartoPy. So this is all exactly the same, but I've got this northeast down call here. And so in our all velocities list, we've got a whole bunch of vector 3Ds in it this time. How does it do that? And so to get out the different components, we'll then get the Y and the X component and save it into a east and north list. and then we'll reshape it so that we can get our U V components ready for plotting. And this time we'll use ax.quiver to plot. So that's the arrow plotting function, and we can see we use our X and Y nodes, so they're basically our longs and latitudes, and our U and V components of the velocities. And add the quiver key is to add the little arrow saying it's 50 million years, so this one here. And to mix it up, we're plotting on an orthographic map. So you can see here, got a whole bunch of velocities and the different sizes going different ways. So it's great. So now we can get ready to make an animation of all of this. And so to do this, here I've just I've done it for one point, and we can just turn this all into a function, and so that we don't have to type out the code over and over again, and call it really easily. So I've created a function, get plate velocities, and I've given myself a little bit of a comment so I know what this function does. And then it's just the same code from before, but I've given it the two options that convert from magnitude, geocentric to magnitude azimuth inclination, or convert from geocentric to northeast down options. By default, it's going to do this northeast, ready for plotting in CartoPy. And so now we can call this function. So first we'll just call it a one-time step. So here's that function we just created, and here's the reconstruction time, 50 MA, and I'm going to use a delta time of 10 million years. So it will calculate the velocities over a 10 million year increment instead of 1 million years this time. And then we'll also reconstruct those coastlines as well at the same time. We'll do the same thing, prepare our output from all velocities, the plotting, and then we'll plot everything again. So here we go. This is, was it 60, 50 MA, and the velocities here. So you can see India's speeding upwards, ready to collide with Eurasia and create some mountain that's really tall out here. And so now we'll add topology. So you notice, it's a bit hard to tell where all the plates are here because I haven't actually plotted anything. And so now we can finally add those topologies. So to add the topologies, we already loaded in those three features, these three files that we need, but we need to resolve them. So we need to get the actual parts of the topologies that are resolved at whatever time increment that we're interested in. And we'll save the resolved ones to an empty list, and we'll save the boundary sections, the individual components. We can explore if they're mid-ocean ridges or subduction zones or fracture zones or whatever, into a different list again. And I'm going to create a output figure directory because we're going to create an animation right after this in the last 7 minutes. Leave on a bang. And so now that we've resolved our topologies to that same time, we'll add a whole bunch of code to sort through these. So for that shared boundary section, I want to see if a file is a GPML mid-ocean ridge type, and I want to separate that out and then plot them as red here. So you can see where there's this dateline wrapper is to try and help make sure things don't cross, you don't get those horizontal lines when things cross that dateline. But you can, and so we basically are looping through getting the points of our topology, and then I'm adding it to my plot as a red line here. And then I'm going to go through and do the same thing, but for subduction zones, and we'll plot them as blue lines this time. And then I'll go through and get a couple more GPML types. So I'll get transforms and fracture zones, and they'll both be K is the shortcut for black. And then everything else that I haven't already, any other GPML type in that in shared boundary section. So here's if you wanted to see all of them, we could comment this line. So anything else, I think there's like some continental rifts and some, I don't know, a whole bunch of things that I haven't ever had to deal with too much because I mostly dealt with spreading ridges and subduction zones. And we'll put them as black, but we'll make them a bit thinner so they're not too obstructive. And then we've got our coastlines again for plotting, so the same as before, and then we'll got the same arrows. I think this is, yeah, exactly the same time step as before. So So here I've changed it to a Robertson plot, but yeah, we can see that we've got some plate boundaries. Here's the India plate speeding up. We've got our mid-ocean ridges where we expect them. We've got our subduction zones where we expect them. And we've got a whole bunch of other lines that are part of the topology files. It's really, I guess, related to the deforming networks as well. And so let's have a look at what are these other feature types. A lot of them are unclassified, which is not the most helpful sometimes. Slab edge, inferred paleo boundary, passive continental boundary, extended continental crust, terrain boundaries. So we've got all of, you could define colors for them individually if you wanted to, but yeah, for here we won't. And so now we're going to create an animation. And so for animations, we tend to just save everything in an increment, say 1 million year increments, and then stitch all those figures together. And then using FFmpeg, or there's a whole bunch of other packages. Someone mentioned a few, one that sounded pretty good the other day that I'd never heard of. And then it's a nice little animation. So here's another animation, another function again that I've defined called reconstruct and plot velocities. So we can do that. We use that same get plate velocities that I did before. This particular function has that reconstruction time and delta time embedded in it. And then it also has this figure part that we just did just straight here. So it will reconstruct everything and then plot it at whatever time. So exactly the same code there. Oh, and it will save everything as part of this. Sorry, I forgot to mention. So before we haven't saved anything. So we can stitch our figures together. We'll save it to a PNG. And my little pro tip for those FFmpeg users dealing with millions of years and stuff is if you make it a little hyphen instead of an underscore, you can actually it's easier to reverse your whole sequence. So instead of when FFmpeg, instead of telling it this is your file name, you basically remove that bit and then you tell it that's your file name and you have the start frame as your oldest time, and it will just know the correct sequence that will go from, interpret as like -200 instead of 200, but it will be from the past to present day when it stitches them together. Or you can easily do it from 0 to 200 at the same time without having to rename everything. So now, okay, let's just test this for a time in the past. So I'll test it for 100 million years ago and see what happens. So it should save something called velocities.png in this folder, velocities figure. There we go. So it looks great. Exactly what I thought it should do. And so now we can make this animation. So we just call this same function, but we just do it in a loop. So here I've created a for loop, and I just want to go for time in range, and so this will be 21, so it will go up to 20 because it doesn't read the last one, so it starts at 0, and it'll then run this with time, so 0, 1, and so you'll see it should print out every time it's doing 1, and we'll have a new output there. Does anyone have any questions there while we wait for these to make? So I know we're about to go over time. Hopefully everyone's still following along or has some kind of gist as to what's happening. So you can see it's saving all our figures out for the different increments. So that's great. You can use this same kind of logic for a different kind of animation. So say I wanted to plot the location of fossils through time, I could make a similar function and save out those figures from the 5th notebook. And then I'll use this FFmpeg line to stitch them together and make a GIF or a MP4 file. So, okay, 16 MA, we're nearly at 20. There we are. So we've got it says 27 there now, so we know that it's finished the cell. Save figure for 20, and I can see I've got figures up to 20 and my 101 MA one I made earlier. And so we're going to use FFmpeg to create the GIF. You can use this package MoviePad. I've left the code in here in case you wanted to do this on your own laptop, but I don't think it's installed on the EdStem environment. And so to use this as FFmpeg here, I have to use some cell magic. So I make this a bash cell. So now I can do all my normal bash commands in a bash cell. If I go to print, I think I should print my working directory. So I'm in home. What a surprise. And so this is the FFmpeg command. I've got both the GIF and the MP4, so we can make both. And so here I specify my file name. So it's my input, my -I is the input. And so I've got a file in velocity figures, and then I'm telling it to read -d MA, sorry, %d MA. And I'm telling it to start from -20 so that it will go from 20 million years to the present. So if you wanted to go from 0 to 20 million years instead, you can add that hyphen there, and it will flip the order that it does things in. Or we could do that actually for one of them. Let's do it for one of them. I'll get rid of this start number. Okay. So now I'm just running that bash cell, and so it's FFmpeg is spitting out all its usual stuff, and it hasn't errored, so that's good. And we should be able to see I've got a GIF and an MP4, so we can display these into the IPython, the Jupyter notebook. So here's my velocities.gif, and then I can also use video for the MP4, and I tend to use MP4s for any presentation I might give. So it's handy to be able to do both if you wanted to. And then let's see. So you can see, time is increasing, so decreasing. So we're going from 0 to 20 in this animation, and you can control your frame rate and all that kind of stuff as well. Does anyone have any questions? We're 2 minutes over, but I really wanted to show you that last bit because it's quite satisfying when you finally get there.
Yeah, it's definitely worth it to get to those animations at the end.
Yeah, don't want to leave like right before doing the animation.
Yeah, that's fantastic. Yeah, I don't think there's any questions coming through, so everyone was following along, I assume. Yeah. So yeah, look. Oh, you go, Nikki.
Oh, I was just going to say we've still got a whole bunch of people on, so we haven't bored everyone to death. So that's good.
Yeah, exactly.
Yeah.
So yeah, that kind of brings us to the end of the course, but the course doesn't have to end here. The EdStem environment is open for another week, so go back and run some of those notebooks again, so you get familiar with pyGPlates, and yeah, you can run your own versions of these notebooks and then just download the data afterwards. Yeah, so
Peter, the notebooks are in GitHub. So I'll share my screen again. So if you go to I can't see my controls. Go away. Zoom. I don't know how to. There we are. Okay, so if I just go to the GitHub, so it's under the GPlates GitHub. It's a public repository, so anyone can see it, and you can see all these notebooks. So here's that velocity notebook that we just did. Give it a second to render, and the data, everything that we used today and yesterday is also in that data folder. So you can download a zip of this and play around it at home. And I've saved the figures in there as well. And I think I even got the animation to save. So I don't know how to get this MP4 one to save, but the GIFs will save in display in GitHub. So that's quite nice. So you can see where you're getting to. And so this will be, up here forever. I don't know. I don't think this is like on the Arctic vault thing that you mentioned, but Ben, but we'll keep it up there. And if you've got questions, like I'm happy to answer as well. It's a lot of information to digest in 3 hours. at once. So
definitely. Yeah. So yeah, thanks for attending, everyone. I think Sabin's going to share around a link later with some feedback on the course. So please feel free to describe what you liked about the course, what you didn't like about the course, and what you'd like to see more of, so that we can tailor this course in the future to the things that the community are interested in. Yeah, so thanks everyone for attending. Yeah, my name is Ben. That was Nicky.
Yeah, I'm Nicky. I'm just reading through just the last questions before we shut this all off. So Peter, I've never used Google Colab, so I can't comment on that. But I guess if you're able to install your own Python packages, that should work, I would think. For local only, definitely it works. So I think Ben and I would have pyGPlates installed on our local machines. We normally use that, which is why we don't know how to get autocomplete working on in EdSTEM. I found it really difficult whenever I've tried to do that compared to my own Python environment. If you're a Mac user, I'm happy to help you get installed pyGPlates installed on a Mac, but that's the only environment I know anything about.
Yeah, I think the only problem with the collabs is that it doesn't have pyGPlates installed on there, so it might be.
Yeah. So yeah, I don't know what the installation process is for those things. Oh, okay. Someone says they've used Google Colab and it's easy. So hopefully it's not too painful. And there will be a pyGPlates Conda environment, which will make life a lot easier soon, hopefully in the next couple of months.
Yeah, definitely.
Yeah. Okay. Well, we're over time. Call it a day.
Yeah, I think so. Thanks everyone for attending.
Thank you so much.
Thanks, Chris, for helping out and fielding comments as well.
Yeah.
Yep, no worries.
Yeah, thank you.
All right. Bye, guys. Take care.